Hello everyone, I'm James and welcome to episode 14 of the OpenGL tutorial series. Today we're going to start working on shadow mapping. If we look at our scene right now, we have a bunch of monkey heads floating in midair. And none of these monkey heads are casting a shadow. That is what shadow mapping will solve. By the end of the video we should get a simple shadow at least under every monkey head. Let's begin.
Let us imagine this is our scene. I simplified it on purpose. The yellow arrows represent the light rays. The light rays won't stop there, they will keep traveling until some object is in the way and they get occluded. As you can see, most of the rays are hitting the floor. However, these 4 rays are being obstructed by the cube. The region on the floor that is not hit by light rays is in shadow.
Let us imagine we are in the light's perspective. What can the light see? Well, the light cannot see any shadows, because everything the light can see is not in shadow. Everything that the light can't see is in shadow. And this is how we're going to make this work. We're going to make a camera in the light's perspective, which will take a photo of the scene from the light's perspective. And the camera will check if something is obstructing. So if something is not in view, then it's in shadow. If something is in view, then it's not in shadow. How do we know if an object is obstructing another? It's actually pretty easy. We already have this framework set up. We use the depth buffer. And if you remember correctly, what gets stored in the depth buffer is always objects that are not occluded by other objects, which is perfect. So we can check if a location, so if we're rendering a certain location, all we have to do is check the distance between that location and the light. If the distance between this location and the light is greater than the depth value in the depth buffer, then this location is in shadow. And that, my friends, is how this works. There is something else I want to explain before we go ahead and start implementing. Our light is a directional light. This light has just a direction. It has no position and no attenuation, which makes it get dimmer by time. It's similar to the sun. The sun has attenuation just like any other light, but it's so huge and so far that it's practically like a directional light. Now, we're going to use a camera to render the scene from the light's perspective. Since the light is a directional light, we're going to use an orthogonal projection matrix. Not a perspective matrix, but an orthogonal projection matrix. So let's go ahead and start implementing.
We'll start by adding this alternate camera in the scene header file. We also need a new frame buffer for the shadow map. This is where we're going to store the depth information from the alternate camera's perspective. In the scene constructor, we'll initialize the old camera. We don't care about the transformation for now. For the projection, we'll use an orthographic projection, as we already mentioned. We need to specify the range the projection can see. I'm going to be lazy and hardcode these values. Now let us initialize the shadow map frame buffer. The first 2 parameters are the width and height. I'll hardcode them to 1024. I'll pass in false for the color attachment, because we don't care about the color buffer. We do care about the depth attachment, so I'll pass true. For the sampling mode, I'll be using GL nearest. This is because we don't care about linear filtering for the shadow map. The last parameter is the wrapping mode. I'll set this to GL clamp to edge. We're going to change the entity's render method. This will take in a shader, and if this shader is null, we'll use the material shader as we've been doing till now. Otherwise, we use the shader we passed in.
So I restructured the entity's render method to do the functionality we want. So we use this temporary variable shader. It's not a temporary variable, but it's a variable, and we set it to the alternate shader initially. If it's null, we set the shader to the material shader. We bind it and we set these uniforms, which will only set when the alt shader is null. And when the alt shader is null, we'll update the materials uniforms. Otherwise, if the alt shader is not null, we'll bind it. And finally, regardless of which shader it is, we'll set the UWVP uniform to the view projection multiplied by the world matrix. Hope you understand. I added 2 new shaders off screen. These are the shadow map shader. This is what's going to be rendered in the shadow map. The vertex shader is very simple. It takes in the world view projection matrix and it multiplies it by the vertex position for the output. In the fragment shader, the fragment shader is also very simple. We're once again using GL frag chord Z, though instead of using it to do some calculations, I'm directly outputting it as a color. So I restructured other things. In the render entities method, I made the render entities method take in the alternate shader, and I'm passing it down in the entity render method. Here, when I'm rendering the water, I'm passing null pointer for the shadow map shader. So no shadow map shader, no shader, it's going to use the material. Same goes here when we're going render entities for the actual scene, and even when rendering to the refraction frame buffer and the reflection frame buffer. I'm also loading the shadow map shader from here, so I added a field for that. It's a shared pointer to a shader, shadow map shader, and I loaded it from shadow map shader vs and shadow map shader fs, basically the shaders that I wrote. Now to test this, what I'm going to do is I'm going to comment out all this code. And instead I'm going to call render entities. This time with the alt camera. I'm going to pass in the shadow map shader as the alternate shader. And I don't care about clipping, so I'll pass false. Now I need to make the alt camera face the light direction. And this is pretty easy. We'll grab the transformation and the rotation of the transformation of the camera, and we'll set it to GLM quat lookat. And what this does is it basically sets the quaternion to face a certain direction, and our direction is the light direction. The up vector we can just hardcode to 0, 1, 0, so an up vector. And of course a semicolon. So let's run and see what happens. And we get absolutely nothing. I found out that the reason for this is because we created our orthographic projection from integers. If we use floats, it will work as intended. So make sure these are floats. Now if we run, there you go. We get our shadow map. Yes, that is the shadow map. We're rendering the shadow map to the screen. And it's working fine. We're seeing all the depth values, and that's awesome. What we need to do now is render we need to render this scene, this image, to the shadow map frame buffer instead. Let's go ahead and do that.
Let us render the scene to the shadow map frame buffer. Next we'll uncomment out the code. If you run now, you should get the same scene as before. Now in the diffuse material class, we'll add the shadow map depth texture. Naturally, we'll initialize it in the constructor. In the update uniforms method, we'll bind the shadow map and send its sampler slot as a uniform, as we do with every texture.
In the diffuse fragment shader, we're going to be sampling this shadow map. To sample the shadow map from the proper location, we need the matrix of the light, so the camera, the alternate camera that is facing the light direction. We need that matrix in the diffuse fragment shader, and that way we can sample the shadow map properly. Let's go ahead and add this light matrix framework.
In the entity render method, we'll add a new parameter for the light matrix. Next, we'll send it as a uniform. In the diffuse vertex shader, we'll take in this light matrix uniform. Now we're going to get the coordinates we need to sample from the shadow map. We'll send these coordinates out as a varying variable. We'll set these shadow map chords to the world position transformed by the light matrix. In the diffuse fragment shader, we'll start by taking in the shadow map chords. We'll also take in the shadow map. I'll store the result of calc_light in a variable, and you'll see why soon. We'll need to do some conversions to the shadow map chords. We'll first do a perspective divide and swizzle the x, y, z components to get a three-dimensional vector. The coordinates need to be between 0 and 1. Right now they are between -1 and +1, so we'll add this conversion. Next we'll sample the shadow map to get the depth value in the map. All we need to do now is check if the depth value in the map is smaller than the current z coordinate. If it is smaller, we'll set the light effect to 0.
I sent the shadow frame depth attachment as the shadow map for the two materials, for both material 1 and material 2. Now we get some errors here because we need the light matrix, not only the view projection. The light matrix is actually pretty easy. Let's first create a parameter for it. So we'll have a const glm mat4, and it's going to be the light matrix. And we're going to pass it in before the view projection because that's how the order I did. Now we need to pass it here in the render entities, and we need to also change the declaration of the function. I almost forgot that. So make sure you change it here as well. And now we need to call, well, with the light matrix. Now to get the light matrix, it's actually very easy. All we have to do, I'm going to store it in a variable. All we have to do is grab the alt camera dot get view projection, and that, my friends, is the light matrix. Now we'll pass in the light matrix as the second parameter because that's where I set it. And for here we'll do the same. And even for the water. Now if we run, we crash and we get an error. I found out what the error is. Shadow map chord here should be shadow map chords. Now if we run, we get weird lines everywhere. However, look at that, we get shadows. Awesome. How can we fix now this problem? It's actually pretty easy. All we have to do is add a tiny offset. I found out that 0.01 worked fine. So here, instead of shadow map chords.z, we do shadow map chord.z minus 0.01. And now if we run, there you go. Look at that. Our scene looks just fine. And now we have shadows. There we go. Awesome. They're very pixelated, but they're still indeed shadows. And that, my friends, is the end of this video. In the next video, we're going to grab those shadows and start making them nice and soft. If you want to be notified when the next video is coming out, please consider subscribing to the channel and hitting the notification bell. With that, thanks a lot for watching and goodbye.